Announcements. We're getting snow later this week. That's announcement number 1. We need the moisture big time. Announcement number 2, quiz 5 is due Friday, which is Valentine's Day, St. Valentine. So you can do it early. You don't have to wait until Friday evening if you have other plans. And then Monday, if you look ahead, Monday is actually a YouTube lecture. It's President's Day. And we don't have it off as a university, but I usually have plans on President's Day weekend, so family plans, so I won't be here. So we're going to do an online lecture on YouTube, which is basically you're just watching the skeletal system lecture, the second one from last semester. That's it. It's a slightly different classroom, same bad jokes, okay? Probably still in a tie, and I'm like, 4 months younger. So there you go. Any questions about that? I'll remind you on Wednesday what that's going to look like on Monday. So you don't have to come here. So you come here, you could do a watch party if you want, but it might be by yourself. Okay. So YouTube lecture on Monday. So we're going to finish up integument today, and then we'll start skeletal system on Wednesday. And this week in lab, you're starting the skeletal system, right? So we're kind of tracking pretty nicely with lab. What did the firefly say to his girlfriend? The firefly. You look simply glorious. You get it? How many from the East Coast know what fireflies are? Yeah, okay. The rest of you can Google it. They're pretty cool. Bioluminescent. What goes all the way around a baseball field but never moves? Not the bases, but you're close. The what? The seam? Okay. The fence. All right. What is the only time that you go on red and stop on green? Go on red, stop on green. When you are eating watermelon. All right. I wasn't going to make fun of your driving. Don't worry. Okay. So part 2 of today. Skeletal system comes up Wednesday. Today we're actually doing the second half of the integument, and I'm going to have to silence my phone because otherwise it's just going to, hang on. There. Otherwise it'll just annoy me all day. Okay, so today we're going to get into a little bit more of the accessory structures in skin. And then we're going to talk a little bit more about some of the clinical attributes that we brought up on Wednesday of last week. So we're into skin derivatives, other things within skin. Now, we've kind of talked some about this when we were together last. We talked about hair and hair follicles, but we didn't get into kind of the microanatomy of hair and hair follicles. We'll talk about that. And we're talking about the different glands, the different type of sweat glands and sebaceous glands. And we'll talk about the nails, which are basically like modified keratin. So that's what's up for this next little section. So we have 3 different types of hair. We have lanugo, which is a fine, unpigmented hair. It's really referred to as fetal hair. And so sometimes when infants are born, they're actually pretty like hairy or furry. And then a lot of that hair falls off, that lanugo hair falls off. And, it's thought to be more of a vestibular characteristic or a characteristic of humanity when we were hairier creatures. And we talked a little bit about that last Wednesday. But that hair, that lanugo hair actually falls off, and it's non-pigmented. Vellus hair is also fine, and it's also unpigmented. And it's primarily the hair that you see in children even infants, but children like pediatric age, as well as in women. It's the fine hair that's on your arms that's not real dark, okay? Doesn't have a lot of the pigment. And then terminal hair. Terminal hair is coarse, long pigmented hair like of the scalp. Okay, so that's, obviously, and there's some pigmented hair. Men have pigmented hair like in their bearded area. Usually their hair is a little darker on their legs and their arms. And there's obviously, it's not 100% one type of hair and 0% the other. There's obviously a spectrum or a range. Now, if we look at the different zones that make up the hair, we've got the bulb. So let's go to the let's go to the bulb first. So the bulb sits in the dermis, and it's where the hair originates. And then the remainder of it, as it propagates to the surface, is in the root, and it's contained within this root sheath, which is an epithelial root sheath, as it makes its way through the epithelium and then out superficially. There's also a connective tissue that surrounds that epithelial root sheath. But again, the bulb originating in the dermis, the root continuing on into the epidermis, and then the shaft. The shaft of the hair is, the part that you actually can appreciate. It's, the outside portion of the hair that's sticking out of the epidermis. That's the shaft. Now, if we look at the hair itself, the outside shaft component, we actually see a couple of different areas. We've got the medulla, the cortex, and the cuticle. So the medulla is the inner portion, and that's a term that we're going to see again and again throughout the semester and actually into next semester in 202. When we look at tissues, a lot of times the inner portion is called the medulla. And then the outer portion is referred to as the cortex. And so you can see in this picture, the cortex is this outer portion of the hair. And this would be the same part as the shaft that's sticking out of the epidermis. But it's not labeling that. It's labeling the portion as it's in the root sheath that's deep into the epidermis. And then the outermost component is the cuticle. That's the outermost component of the hair shaft. So let's back up to the medulla. The medulla is made up of loose, arranged cells and air space. That's the innermost portion of the medulla. The cortex is densely packed keratinized tissue. So keratin, you remember keratinocytes make keratin, and keratin is what? What kind of a protein is it? What's that? What kind of a protein is keratin? Is it elastomeric? Is it structural and stiff, rigid? Structural, stiff, and rigid. Okay? It provides a lot of strength to the material. So I already kind of forecasted that if you tap your nail bed is essentially keratin. And that's why it's so hard. Now, the cuticle is one layer of scaly cells, and it's the outermost part. It's like overlapping cells that look like a sheet of armor. And it gives a lot of the strength to the hair itself. Now, why do I have a picture of a rhinoceros? And I alluded to these horns in a lot of organisms are like modified hair or modified nails. So they're made up of, keratin in a very specific architecture, and they're extremely hard. Hard enough to pierce, enemy prey or predators if they're trying to stay away from them. So hair, a lot of keratin. On the keratin theme, let's move to the nails. So nails are a modified epidermis. It's hard keratinized layers in a nail bed of epidermal cells. And we've got three parts. We've got a root, a body, and a free edge. Now, the root is best shown in this cross-sectional diagram down at the bottom, where you can see that the root is underneath where the skin is. So it would be right here. And how many of you have lost a nail? Okay. Drop something on your toe, hit your thumb with a hammer, right? It turns black and blue. It throbs pretty aggressively. In some cases, we'll actually have to drill out the nail to relieve the pressure because it's so uncomfortable for the patient. But if you do trauma to the nail root, that's when you're actually going to lose that nail. It's going to fall off. And as long as these regenerative cells aren't completely damaged, that nail will grow back, and it takes about 8 weeks for it to fully grow back. It's basically modified skin. So the turnover of the nail is just like turnover of your skin. And it falls off, and there's a period of time where you don't have a nail, and it looks pretty gnarly, but for the most part, it grows back. Now, sometimes it'll grow back a little awkwardly, or it may not. It may have a scar in there. And part of that's because the trauma to the nail root is so aggressive that you've damaged some of those cells, and they don't actually replenish everything that you lost. In some cases, it doesn't grow back at all. So one of my daughters was a ballerina and did a lot of ballet professionally, and had a lot of feet issues, but she lost a lot of toenails, and it was just really kind of hard to see. But some of you know folks like that, or athletes, a lot of long distance runners. It's the same kind of thing. They lose a lot of toenails because we're not really designed to run that far. You know, that's kind of how that works. I try to explain that to my daughter. We're not really designed to dance that way, but she didn't want to hear it. So the nail root, and then we have the body. That's the part that you kind of paint. And then we have the free edge. That's the part that you clip or you shape and you sand or whatever. Okay? Now, this term cyanosis is a clinical term from the word cyan. What do you think cyan means? Blue. Yeah, cyan is a printer ink cartridge, right? Or a laser printer. Cyan is the blue that's in your printer. So cyanosis is a blue color to the nail bed. So when you clinically have patients that are either hypothermic or low blood pressure, poorly perfused, one of the places that you evaluate is their nail bed to see if it's actually a bluish color. And that'll give you a clue because the nail is pretty translucent, as long as it's not painted. It's translucent, and you can actually appreciate the underlying vasculature, and that's basically your distal extremity, right? So if you're a little cold or underperfused, you're not going to send all the blood to the tips of the fingers, and so they'll be a little cyanotic. Question? What's the point of nails? So they're for protection. They provide a lot of dexterity in other organisms that have nails, not necessarily us. They're very sharp. You think of like cats and dogs or other organisms where the nails will either be protection or help them with hunting or gathering or climbing, like squirrels. So, for us, it's a remnant of the evolutionary process, but they do provide a lot of benefit for the tips of your toes and your fingers to protect them. And so hopefully that answers your question. I mean, that's the thought, is that other organisms use it. I mean, we don't climb trees every day. We don't have to fight off predators. I mean, we're kind of at the top of the food chain. But in other organisms, that's the case. Let me back up one slide because I wanted to touch on a clinical correlation that was brought up last week, and I'm going to tie it into hair. So let's talk about gray hair first. So graying hair is when the hair starts losing its ability to make what pigment? Melanin. And that's what gives the shade of hair color that you see in this room. Different concentrations of the melanin or different types of melanin. And so when the melanin production starts to drop as an individual gets older, because the hair is a loosely packed of cells and air, there's more air in there, less pigment, And you get a gray appearance because you have some light that's passing through the air pockets and there's no dark pigment. Then when white hair comes about, you don't make pigment at all, and it's basically the hair is almost translucent, and it gives it in the refraction of light coming through the hair gives you that white color. Okay, so that's how that happens with graying hair. The other melanin analogy or clinical correlation is this vitiligo that somebody brought up, where these patients lose in their skin. They have regional areas where they lose melanin production. In individuals that have darker skin tones, it's more obvious because the melanin is basically not being produced. And so there's no pigment in that area of the skin. And right adjacent to it is typical pigment for that individual. In lighter skin-toned individuals with vitiligo, it's not as obvious that in darker individuals. Make sense? Okay, so that's our sort of couple little clinical correlations that we started talking about last week that I wanted to finish up this week. Okay, let's move into other accessory structures in the skin. And again, I know in lab there's a lot of overlap, but I think that's helpful. I think it helps to reinforce. And I talked to one of your colleagues in office hours today, and they didn't have lab last week because there was some mix-up. So if that was your section, sorry about that. I don't have a lot of influence over the lab anymore, but I will follow up and just see what the plan is there and maybe make an announcement. I imagine it's going to be open lab time is what they're going to suggest. Oh, you're doing it online. Okay. Well, the nice thing is that we're having it in person here, which is a lot of reinforcement of what you missed in lab. You don't get to see the models, those kinds of things. So now we're going to talk about some of the other accessory structures in skin, like sweat and sebaceous glands. So hopefully you can appreciate when we started this unit, we talked about the integument being an organ. And so this organ is multiple tissues and multiple structures making up the organ for multiple purposes and multiple functions, right? So now we have hair, we have nails. We asked about what's the purpose of nails, right? Now we're going to talk about these glands. And obviously sweat glands, what's the purpose of the sweat gland? Cool you down, okay? But it also helps to release waste products, okay? And these other glands are going to release oils like sebum and help with waterproofing. So we'll look at some of these things. And then there's modified glands that we're going to look at. So we'll start with these sweat glands. Another name for it, aka also known as sudoriferous glands. So you might see that in some textbooks. Sweat glands are sudoriferous glands. This terminology of insensible sweat. Insensible sweat is inefficient transepidermal water loss. So throughout the day, especially in the dry Southwest, you're actually just losing water even though you're not hot. Even though you're not sweating, you're actually losing water because the outside environment is so dry here. Okay, so that's the term for that is insensible sweat. It's insensible because you're not sweating for a purpose. It's just the inefficiency of the skin. Nothing in the body is 100% efficient. So, for example, this is next semester, but what do you think the efficiency of the heart is in a young, healthy, athletic individual like what's in this room? What's the efficiency ratio of the heart? Any guesses? No guesses? 90%. Thank you for taking a step. I wish it was not 90%. It's about 70. It's a little higher, probably about 75 to 77%. And the rest of it is wasted, right? And then that ejection fraction or that percentage of efficiency of the heart just starts to diminish as you age. So there's nothing in the body that's 100% efficient, including the skin. So that's the insensible sweat terminology. So 3 types that we're going to look at: merocrine, apocrine, and modified. So the histology on this particular slide is showing a merocrine gland. This merocrine gland has another name in other textbooks called eccrine. I will probably stick with the nomenclature of just a sweat gland. I won't refer to them as sudoriferous just to try to minimize confusion. I'll try to stick to the nomenclature of merocrine, apocrine, and modified. In modified, we're going to see two different types. So back up. So the merocrine sweat gland is quite interesting because the merocrine sweat gland is actually the most common. It's very abundant on the palms and the soles of the feet as well as your forehead. So when you get nervous, okay, and you have sweaty palms or you have, perspiration that kind of starts to bead up on your forehead, those are all merocrine sweat glands. They secrete fluid on their apical side via exocytosis. So that's actually fusing the membrane of a vesicle with the outside membrane and dumping the contents. It's controlled by the sympathetic nervous system. That's why when you get stressed or when you get anxious, your palms get sweaty. And where does sweat come from? I just want to pose that question. Where does it come from? How does the sweat gland actually manufacture sweat? See the structure right here in this cartoon drawing. And then here is the histology of the sweat gland. And these are secretory cells, right? They're cuboidal in appearance, much like the kidneys. They're releasing fluid. Where do they get their fluid from? Any guesses? Blood. Is that weird to you? Is that surprising? So the sweat gland actually filters the blood and pulls out waste products like ammonium and salts and releases them onto the surface of the skin, along with some water. And that's the wet part that you see. But after you're done working out at the gym and you hang up your gym clothes, and if you've not washed it and you come back the next day, what do you see? You see white stains, right? From the salts and the other waste products that are being filtered out of the blood. So in a way, they're filtering the blood to screen and get rid of metabolic waste products. That's what your sweat does. So the sweat is actually filtered blood. So is it possible then clinically to have a situation where you actually sweat blood? Yeah, it is. Physiologically, it happens, and it's been documented in medical literature of patients that they're so stressed out because it's under sympathetic nervous system control, and they traumatize under the stress with corticosteroid release and lyse cells within the merocrine sweat gland, and now you have filtrate blood that actually moves to the surface of the skin. Pretty crazy, huh? So, merocrine sweat gland, most common, palms, soles of the feet, forehead. Okay, next up, apocrine. The apocrine are primarily found in the armpit or the axillary area, the groin, the anus, around the areolar of the nipple, and in adult mature males in the bearded areas of the face. So these are larger glands. The ducts empty onto hair follicles, in contrast to merocrine, which are just found everywhere. And they secrete sweat as well as fatty acids and proteins. The apocrine glands secrete more than just filtered blood. So you have fatty acids or fat, and you have proteins. Now, there's bacteria that lives on your skin, right? We talked about that. That natural bioflora, it's almost like a fingerprint signature to you. Like if we swabbed your skin and we ran an analysis of the bacterium that was growing on your skin normally, it would be unique to you and not anything like anybody else. Pretty crazy. Well, that bacterium feeds on those fatty acids. And as they feed on those fatty acids that are being released out of apical sweat glands, they break down the fatty acids, and their byproduct is an odor. And that's where we get body odor from, BO. Okay, that's that symbiotic relationship. We give the bacterium food, they give us odor. Yeah, you're like, huh, that seems like an odd trade. Okay, so your odor is unique to you. Do you know how you know this? How many of you have a dog? Okay, it's most obvious with dogs. I know I'm not like anti-cat, but you know it's most obvious. How many of you have family dog? Raise your hand. Okay, family dog. So when a new person comes to the house, what's the most embarrassing first thing that your dog does? Sniff somewhere in the groin, because that's where their name tag is. That tells that dog, your dog, is learning that that is a new person. And when they goose you, right, they're just saying hi. They're like, oh, I know it's you, John. Like, Leslie, it's good to see you home, right? But that's why they're so drawn to, I mean, if our armpits were a little closer to the ground, they would sniff that. But, you know, other aspects are closer to their nose. So apocrine, these locations is where this odor that makes us is very apparent. Okay, so modified sweat glands. There's two types that we need to talk about. The first one is the mammary sweat gland, or breast tissue. And this, here's histology of apocrine, by the way. And you can see this is the apocrine sweat gland onto the hair shaft. This one is just to the surface. Do you see that? This one's onto the actual hair shaft, the apocrine glands. And these apocrine glands have a bigger lumen because they're putting out more stuff, putting out those fatty acids as well as those proteins. The modified sweat glands, breast tissue in females is a modified sweat gland. And it is under production during pregnancy to manufacture filtered blood in the form of what? Milk instead of sweat. So there are things for pregnant women who are going to be nursing that they have to be very mindful of, because if they eat certain foods or they consume certain drugs, medications, and they're in the bloodstream, and then you filter the blood to make milk, then you transfer some of those medicines or drugs to the infant. Does that make sense? Same thing with alcohol and all those. That's how it gets into the bloodstream of the nursing infant. The second one, ceruminous. That's how you pronounce this. Ceruminous. Ceruminous glands. Where are those located? Any guesses? In your ear. And they are a modified gland that makes what? Earwax. Keep things out of the ear canal. We won't revisit that until the very end of the semester when we talk about special senses, but we'll talk about why that's so important. I mean, you don't want debris getting all the way to the eardrum, because you know that the tympanic membrane, that would actually cause irritation. So we have very sophisticated cells that line only in this location, which is crazy. Only in this location are you making earwax. But it's just a modified sweat gland. It's pretty cool, huh? Okay, so the holocrine glands are the last gland that we need to really talk about. And these are sebaceous glands making a product known as sebum instead of sweat. So what is sebum? Well, sebum is a lipid that helps to waterproof the skin. In fact, you know, one of the things that's kind of funny in our culture that we do, which is very different in a lot of other cultures, is so Americans in the West, we tend to bathe a lot more than other cultures, okay? And so when we bathe, especially in the Southwest, your skin gets pretty dry. So then what do you do after you dry off before you put your clothes on? What do you apply? lotion, have you ever read the back of the lotion container on the ingredients? Manufacturers will add sebum, but not human sebum. Usually it's like sheep or cow. So just keep that in mind the next time you shower. You're taking off your natural sebum, and then you're going to put on sheep sebum afterwards, right? It smells nice and it feels great. But now that I told you that, read the label and see what kind of sebum you're applying, right? So we probably do over shower in this country. And then we buy another product, which is, some other animal's sebum, not ours, which is kind of weird. But these sebaceous glands, a Hollican gland that's shown over on the far right versus American gland, these are fusing these vesicles with the membrane via exocytosis. The Hollican gland actually just sort of ruptures the entire cell and dumps its contents. And that's how it gets the sebum to the surface. And you can see those arrows coming to the surface and then spreading out. And that's what our natural moisturizers are, our natural moisturizers. So from a dermatology standpoint, and this is true with pets, if your pet scratches a lot, your vet's probably going to be asking you like, well, how often are you bathing your dog? You're like, well, every day, Well, the dog's sebum is not being replenished fast enough. So they'll probably tell you, decrease the intervals of bathing your dog, and the itching will probably reduce. Same for patients. A lot of itchy skin, a lot of dry, itchy skin, a lot of times it's less showers. Okay? So sebum and sweat. The other thing about these sebaceous glands is a lot of these can get plugged up. Bless you. A lot of these can get plugged up. And now you have this oil fat that's trapped. And so it could be a sweat gland or it could be a sebaceous gland. If it's a sebaceous gland, either one of those situations could be the situation of acne. Okay? In these cases, a lot of times these are big dermal cysts. People that have really aggressive acne, that have really large dermal cysts, a lot of that is targeting these Hollican glands or these sebaceous glands that are being plugged up. Questions? All right. So we're going to kind of shift gears a little bit. We're going to talk a lot more clinical situations that I think a lot of you might, be more interested. We're going to talk about tattoos. We're going to talk about burns. We're going to talk about skin healing. I'm going to give an anecdote of some old technology that I worked on. And that's kind of how we're going to wrap up. And then I'm going to show you a video of some really cool new technology that's not mine, but it's out there. And I think you guys will find it quite fascinating. Okay, so some common skin-related diseases. Some common skin-related diseases that we need to walk through. First one is erythema. Okay, erythema is from the Greek word eros, which means what? Red, a redness of the skin. So the clinical term, bless you, the clinical term erythema means skin redness. It's usually a sign of inflammation, erythema. The next one is jaundice. Jaundice is a term that means yellowing of the skin, a yellowish pigmentation. Could be jaundice of the whites of the eyes as well. It's usually an indication that something's wrong with the liver. So young infants that are born, newborns, that are born premature, when the liver is not fully operational, they'll be slightly yellow in color. They'll be jaundice. Alcoholics, at the end, when they have cirrhotic livers, they also have failing ability to remove toxins, and so they'll be jaundice in color. And it's usually the whites of the eyes that we'll see. Now, the jaundice is because the blood the red blood cell has a specific lifespan in the bloodstream, and every couple of months it goes to die off, and it's excreted, and the liver helps process that. And one of the byproducts of breaking down red blood cells is a compound known as bilirubin, and it's a reddish brown color, like the color of a red blood cell. Well, that bilirubin then is excreted in the fecal material. which is what gives stool its color. Otherwise, if it didn't have bilirubin in it, it would be essentially like a grayish, like a gray color. But the reason poop is brown is because of the bilirubin. So if the liver is not processing the red blood cells well, the red blood cell bilirubin level, the byproduct, stays elevated in your bloodstream, and now you get this yellowish color in your skin. Okay, jaundice. But it's a telltale sign clinically that something's not right when the skin looks a little yellow or the whites of the eyes are a little yellow. Pallor. Pallor is, like it sounds, pale in color, not well perfused. So there's a reduced amount of oxyhemoglobin or oxygenation of the blood, and you have a pale color to the skin, pallor. Albinism. Albinism is this top middle child is an albino, and there's a mutation in albinos where they, and albinos is from the Latin albus, meaning white. So their skin is absence of coloration, truly absence of color. Some of our Nordic friends are like, hey, I have pretty pale skin. There's still melanin being produced, but it's highly diluted and it's very low. But albinos don't actually make any pigment at all. So they're very, very careful about going out into the sun because they have no UV protection. So this is a defect, a congenital defect, partial absence or complete absence of pigment in the skin, hair, as well as the eyes, due to the lack of an enzyme known as tyrosinase. And tyrosinase takes tyrosine to melanin. That's the amino acid that is used to make melanin, is tyrosine. The second to the last, hematoma, that's a fancy word for a bruise, and that's what's this bottom picture with this gentleman with his pants down, but he's standing at just the right angle so you can see the bruise and nothing else. Okay? All of you have seen something like this on your own body, I'm sure of it. You've bruised yourself. That's pretty aggressive. And again, that's where the blood becomes extravascular. It leaves the vessel. You have fractures of the vessels in the skin, in the dermis. The blood leaves out into the connective tissue, the extracellular matrix, and it coagulates and it sits. And it's red in color because of the bilirubin and the heme, the iron. And then over time, it starts changing colors into funky shades, right? Like yellows and purples and sometimes greens. Because of the way that the body sends macrophages in to clean up the debris, you're getting different stages of the breakdown of those pigments. Hematoma. Then the last one, hemangioma. And some of you asked this. I had a few questions on Wednesday about, just birthmarks. A hemangioma is a birthmark. And hemangioma is an abnormality in the dermis under the skin, right? Dermis, the second layer of the skin, or just beneath the epidermis. And you have a overproduction of blood vessels that are in that tissue. And when they become highly perfused, like when the individual is warm or excited or hot, more blood will flow to that region, and the birthmark or the hemangioma will redden. And then when they're, calm or they're cold, it might actually fade. So a lot of times, if for cosmetic reasons, usually hemangiomas will be treated with laser therapy. We'll coagulate, we'll just cauterize that area of the vasculature bed so that you don't get perfusion anymore, and it pretty much disappears. Okay. Hemangiomas, this is, anybody know who that figure is on the far right, upper right? He had we call it a port wine stain on his head. You see the hemangioma up top? He was that was his calling sign. Everybody knew who it was. He was a figure in the former USSR named Mikhail Gorbachev. So this was President Ronald Reagan and Mikhail Gorbachev were the ones that did that peace treaty in the 80s. Okay, probably before any of you were born, but That's who that is. And that was probably one of the most famous hemangioma birthmarks, is Mikhail Gorbachev. So the red birthmarks are hemangiomas. The brown birthmarks, like moles and freckles and those kinds of things, we call these like stork bites, right? We have all these cute names for them. But like moles and freckles or brown birthmarks are what? What are they made of? An overproduction of melanin. Yeah, just at that time during development. That's it. Okay, let's talk a little bit about skin cancer. I mean, honestly, the stuff above wasn't really that serious. This is getting pretty serious. 3 different types of skin cancer I want you to be familiar with: basal cell carcinoma, squamous cell carcinoma, and malignant melanoma. And I've listed them in order of severity. Malignant melanoma being the most severe. So the first one, the basal cell carcinoma, is the most common. You see the top right picture is a basal cell carcinoma, and it's right on the temple in this individual. You can see it's raised. It has a reddish appearance to it. 3 out of 10 Americans will develop basal cell carcinoma in their life, and 8 out of 10 skin cancers are actually this type of cancer, basal cell carcinoma. It's the most common. Metastasis is rare, so it's the least dangerous. Metastasis is just a word that means that it breaks off and it goes other places. It spreads. So usually it's not a spreading kind of cancer. It's pretty contained. It's relatively easy to surgically remove it because it doesn't really leave its space. What cell line do you think basal cell carcinoma is a mutated form of? Stratum, what layer? The basal layer. That's where it gets its name. Next one, this picture of this individual's hand. You can see squamous cell carcinoma. Second most common, has a higher risk of metastasis than basal cell, and can be any of the layers that are squamous in phenotype. So it's obviously not the stratum basale, but it's anything that's superficial to that. It wouldn't be the stratum corneum because it's dead tissue, right? So it's got to be those first layers of spinosum granulosum, squamous cell carcinoma. How does this happen? Well, when we have DNA that's hit by UV light can cause mutations and cause damage in the DNA or a nick. If that nick or that damage in the DNA is in an area that controls replication of the cell, now all of a sudden the cell is not under regulatory control anymore. It's going to replicate without any control systems in place. And as it replicates, it doesn't stop and it keeps growing, and that's basically cancer, is your own cell that has mutated and now it's replicating out of control. Make sense? So normally your cells will go through a very specific process of when it's going to go through cell division. And you learned all that in basic bio. And so the control mechanisms in your body that control when it divides and when it stops, right? Like in gap 1 or gap 2, cancer cells, because they've mutated, they never pause. And they just replicate out of control. We call it, being immortal. We talked about this with Henrietta Lacks, right? This immortalization of cells just means that they divide and they replicate forever. And that woman's cervical cancer cells were captured in the 50s, and they're still replicating today. Okay. The last one is a malignant melanoma. It's the most severe. The malignant melanoma is more rare. Not as many people have it. It's found in skin, the colon, and the eye, and it's the most lethal. And what cell type do you think is mutated with a melanoma? A melanin-producing cell, which would be called what? A melanocyte. That's exactly right. So they're much more brown in color, a dark brown or black. They tend to be raised, and they're highly malignant. So they metastasize and they go other places and break off. And so the malignant melanoma is if you're like someone who has a lot of moles, as you get older, you're going to want to keep track. Your dermatologist, your primary care physician, say, let's watch those moles just to make sure they don't change in shape or get raised or start getting tender or a little bit painful, because those are areas of high concentration of melanocytes making melanin, and you don't want them to break off and go other places. Does that make sense? And so that's why dermatologists are always watching people that have a lot of moles, like on their back or their face or their neck or their legs or whatever. So best practice. Okay, let's talk about art. How many of you actually have a tattoo in this room? I mean, as I've been doing this a while, and the number of hands that go up is increasing steadily over time. I think tattoo parlors would have been a good business to invest in 20 years ago. I think I missed my opportunity. Okay, so some of you have some. How many of you don't have one that you're thinking about getting one? Okay, I might change your mind here. Okay, so these are permanent ink markings. Nothing's permanent, but we say that they're permanent. It's ink that's literally injected into the skin. And if you had to guess, what layer do you think we put them in? Why? Why the dermis? Long-term retention. There's no real turnover, right? I mean, if you were the tattoo parlor that only put it in the epidermis, your patients would be coming back like every 8 weeks going, dude, you got to redo this. So you'd make a lot of money for a while, and then you'd have no customers. Okay? I was going to ask that was my next question. You just read my mind. $5 later, I'll tip you. Why not into the hypodermis? Bloodstream, putting ink in the bloodstream, that doesn't sound like a good idea, right? Now, there's vasculature in the dermis, but it's not as big, and it's not as prevalent as it is in the hypodermis. So that's why we try to target the dermal layer. So the needles and the depth of penetration are set so that you deliver into the dermal layer. Okay, now you can see here, here's our skin profile. Here's our surface, here's our epidermis, here's our dermis, here's our hypodermis. Here's where the ink goes. The needle's delivering the ink. Well, you can get these removed. You can get these removed, and you can vaporize the ink by delivering energy in the form of laser technology that will have the highest energy setting at a certain depth where the ink is. Okay, so you guys want to see this video? Oops. Never mind, not going to see the video. Just kidding. – 20-year-old tattoo, not individual. She's laughing at him. I'm going to make you watch the whole thing. About halfway done. Halfway. All right, almost done. Stay with me. All right, we're done. So, here's some examples. These, very common for these medical spas to be using laser therapy to do tattoo removal. Some parlors will modify tattoos, like you had an X They'll try to make it into the new name, right? So think about that when you get your tattoo with your partner. You want to make sure that there's not too many vowels in there because it's really hard to make new names out of that. So you can see that there's some scarring on the far right, right? Some scarring that takes place. It's not completely perfect. But that's how tattoos are delivered. That's how tattoos are removed. Will that technology improve? Probably, as time goes on. Yeah. Oh.
The tattoo artist just and didn't follow the stencil at all. But actually, they told me mine shouldn't have any scarring because I think I have to go in 12 times.
Yeah.
And it's way less.
Yeah. So now what they're doing is, like you can see in that older image, they're hitting it with a lot of energy right in the beginning. And so now what they'll do is they'll back off the energy, and they'll do, like you said, 12 treatments of lower energy to minimize the trauma to the tissue and really just try to focus on vaporizing the ink. So that's more expensive procedures. Should be a little less painful or uncomfortable, I should say. But still, you're putting energy into the dermis, and so kind of plan on that. It's gonna be kind of angry at you the next day. There's no question about that. Yeah. Yep. Yep. Yeah, so it's a great question. So our those of us that have darker shade of skin, when it's exaggerated as you age, by the way, too. So getting a tattoo removed when you're younger is far better than getting it when you're old, removed when you're older. So a couple things. The healing process when you're younger is much better. And the production of melanin is more regular and consistent when you're younger. So in darker toned skinned individuals, having that remodeling that's taking place at a younger age, you'll have less of a scar, less of a blanching. It'll be a little bit more uniform. Yeah, all these things are in play. Yeah. Okay, let's talk about skin damage in a different angle. Let's talk about burns. And how many of you are going to be clinically focused as time goes on? Okay, quite a few of you. So you're going to unfortunately run into patients that have severe burns. I mean, this is tough. This is really tough to see. So we have the different categories of first, second, and third degree. First degree, and it's based upon the severity of the damage. So first degree, really only the epidermis is affected in first degree. Red, painful, and you get edema, which is a fancy word for fluid swelling or tissue pooling with water. So you'll get swelling that takes place. That's what edema means. But it's only at the epidermis level. Second degree is the epidermis and part of the dermis. And the reason that you know that you're in a second degree situation is you'll get blistering of the skin, where you're starting to get the skin separating and you're getting pockets of fluid, serous fluid, as the tissues separate. Second degree. And then third degree is epidermis and dermis all the way through and through, full thickness burn. And it often requires grafting, skin grafting. And you have a lot of fibrosis, which is a fancy word for scarring. And then you have some disfigurement that can take place in these patients. And you may even be worried about losing the patient if it's significant square area, surface area of the body. And then we talked about this earlier, your first thing is water loss in these third degree patients. If they're 80% of their body is third degree burns, a lot of times these are motor vehicle accidents, and first responders can't get them out quite fast enough. They had to use the jaws of life to pull them out. Cars on fire, those kinds of things, or burning buildings, those kinds of things. And then after you stabilize the patient with water loss, you worry about infection control because of the barrier of the skin being gone. So what we do here in third degree, well, in all of these, but primarily in third degree, is IV nutrition and fluids. And you can add in antibiotics in the IV to try to manage any kind of infection control. And then a term that's a weird term, it's called debridement. Debridement of the tissue, of the skin that's damaged. That means getting rid of the dead necrotic tissue. So debriding a wound, debriding, so D-E-B-R-I-D-E-M-E-N-T, debridement. It's spelled like debridement, but it's pronounced debridement in wound care. So when you debride a wound, you can do this a couple of different ways. You can do it with mechanical agitation, which is a little bit painful, removing the skin that's dead. You can do it with chemical enzymes to break down dead tissue. There's historic ways that it's been done in different cultures. In fact, some cultures have used maggot therapy, which is very effective for debriding a wound. Adding maggots into the wound bed, they will only feed on dead tissue. They will leave healthy tissue alone. So if you watch any of those movies, that's like a real thing. Works pretty well. FDA doesn't love it, so we don't do it in America. All right, I am going to shift gears to a little video. We got a couple of videos today. This one's on sunburns. And sunburns have first, second, and third degree, believe it or not. Usually third degree is pretty rare. But second degree burns with blistering, I mean, come on. How many of you know you've had a second degree sunburn? Yeah, you've had blistering, right? Raise your hands again. Wow, yeah, it's our lighter shaded folks. Ah.
Garden or on the beach, and then a couple days later, my skin starts peeling.
Yeah.
Seriously, pretty gross. Not exactly the effect most people go for when they sunbathe. But what really happens when you get a sunburn? I'm Anna Rothschild, and this is science. Most burns occur if you come in contact with something hot, like when you scald the roof of your mouth on a slice of pizza. But sunburns are actually not caused by heat. Sunlight is made up of a bunch of different types of radiation. One of them is infrared radiation, which is primarily what makes sunlight feel hot. But there's also visible light, which allows us to see sunlight, and then there's ultraviolet radiation. Ultraviolet, or UV radiation, is what causes a sunburn. It can wreak havoc on skin cells by disrupting important molecules like DNA. So your body does its best to protect you from it. When UV radiation hits your skin, pigments called melanin absorb it and shield your DNA from harm. Now, melanin is present in our skin cells all the time. It's what gives your skin its particular color. It's created by special cells called melanocytes, which then distribute the melanin to other cells called keratinocytes. Those are the most common cells in your outermost layer of skin. When your skin is exposed to UV, the melanocytes ramp up their melanin production and also transfer more melanin to the keratinocytes. This happens to varying degrees based on your genetic makeup, but that's why your skin might turn darker or tan if you're out in the sun for a while. But the melanin defense is far from foolproof. Regardless of how dark your skin is or how much you tan, some UV rays can sneak past. And when they do, they can damage your DNA. This can actually happen in a few different ways. Sometimes the radiation will directly zap your DNA, damaging it in just a trillionth of a second. Alternatively, UV rays can do something more sinister. They can actually turn your melanin against you. The radiation can make your cells produce these harmful molecules called free radicals. Now, this is a little bit complicated, but essentially, the free radicals excite an electron in your melanin. I'm excited. Melanin then bumps into your DNA and excites an electron there. I'm excited too, which can cause the DNA to change. Regardless of how it happens, once your cells are damaged, they start producing warning molecules.
Okay, you get the idea. questions on kind of how that works. And one thing that she kind of said that I want to make sure we touch on is, this sort of, I think, false sense of security that if you tan really well, or if you have very dark, beautiful, dark skin, you are still subject to UV radiation. Even though you don't sunburn, the UV rays can cause damage to your skin. So it's something, to be thinking about. And as skin ages, the big reason that skin looks like old skin is because of UV damage. And so there's more and more skin awareness these days with cosmetic companies putting UV blocking agents within their cosmetic products. There's a reason for that. So just be mindful. If you're very subjected to burning, please use sunscreen. And even if you're not, it's just a good practice, especially in the Southwest. Okay, when we get damage, now we're talking not just about UV damage. We're going to shift gears a little bit. We're going to talk about wounds. Okay, the skin can repair itself in two different ways. Skin can actually go through a process we know as regeneration. It can regenerate the tissue back to normal. And if it has a regenerative process, there's going to be far less scarring or fibrosis. If the wound can't regenerate itself completely, it's going to go through a process known as healing or fibrosis, which leads to a lot of scarring. And these are really the only two options that we have. So we talked about skin grafting in the burn segment. So how does skin grafting happen? Well, a lot of times what we'll do is we'll harvest skin from a non-damaged area. We put it through a device that actually meshes it to take a small square centimeter area and make a large square centimeter area. And so in skin grafting, a lot of times what's left, this pattern, this honeycomb pattern, is a result of the meshing that took place in order to expand the skin graft. And that's an autograft. That's from the same patient. You can do cadaveric skin grafting where you don't have to mesh it. So you have people that donate body parts. You can donate skin and you can use it to heal and you don't have the meshing. So that's how skin grafting works. Now, in this little segment, I'm going to walk through this and I'll tell you what I want you to know. But I just want to tell you a little story of this is my first company that I worked at back in the late 90s. And we were in Southern California and we're going to focus on this one, a number of different products, but we were making a tissue engineered skin. And this technology is still on the market today, still being sold. So what we did is we took a mesh, a bioabsorbable mesh, and we grew fibroblasts on it, skin fibroblasts. And they grew and released their matrix components. And after a few weeks, you would have a completely tissue engineered piece of skin. Now, where did we get fibroblasts, human fibroblasts that were donated that were very young? What was our source of fibroblasts? Any guesses? They're from skin, young throwaway skin that was discarded. Any guesses? Huh? Not dead people, alive and kicking, alive and kicking. And we only got it from boys. Yeah, I see some jaws dropping. So these were donated foreskins that were throwaway skin. So we harvested fibroblasts and grew a tissue engineered skin. Here's what it looked like. Well, you remember, you guys will probably never forget that now, huh? Here's a fibroblast. Here's a piece of polymer, and they're growing, making a skin graft. So this changed hands. This company changed hands a few times, and the last I knew, it was in the hands of Organogenesis, and they're still selling it today. Okay, so this is some of the clinical data. We actually made this replacement skin for diabetic foot ulcers. So this is the bottom of a foot. This is an ulcer that's been open for 6 months. And we laid down this skin, and in 10 weeks, it was completely healed. Pretty cool. This is how it worked. So this is that same heel. This is a laser Doppler study at like 1 week, 3 week, 5 weeks. And the areas that are blue are low blood flow. The areas that are like red and yellow are higher blood flow. You can see weeks later, there's more blood flow in the middle of the wound bed. And remember, blood flow is really important for healing. So we're increasing blood flow by increasing this molecule known as VEGF, okay, vascular endothelial growth factor. Here's a control scaffold. Here's a scaffold, we called it dermagraft. Here's a scaffold that had the fibroblast grown on it, the foreskin fibroblast, and you can see all of the new blood vessels, okay? So on the exam, if I ask about it, I want you to know the source and that it was a fibroblast, because that's what's relevant to skin, right? Yeah, and some of you are like, that's so weird that you guys got that from. You know what? You can take those fibroblasts. We had only 2 donations necessary because those foreskin fibroblasts will replicate and divide, and we could cover the planet of the Earth with fibroblasts in about 6 months from 2 foreskin. Promise. This is pretty gory, okay? So I'm giving you a little warning if you're a little squeamish, but this was an individual that had an accident with a chainsaw. It slipped and it hit him in the face. Okay, are you ready? And that's what presented at UCL Medical Center. And so we decided that we were, the surgeon decided they were going to close. They closed. They packed inside of the wound bed with dermagraft to try to promote healing. This is the individual a year later. Now, what I want to ask you, and turn to each other and talk, was it regeneration in this individual or was it fibrosis? Regeneration, complete restoration of function. Complete restoration of function. Is that regeneration? So skin's going to have sweat glands that come back. Hair is going to grow back. No scarring. Is it complete regeneration or is it fibrosis or is it some, you tell me. Okay, let's hear it. Let me hear some. Let me see a hand of, you think it's fibrosis, like healing with scarring, or do you think it's complete regeneration? Let me see a hand. Who wants to go? Andrew?
Mix of both.
Is it a mix of both? Look at this diplomat right here. Crossing the aisle, make no waves, everybody's a friend. Why? Why is it both?
He's got hair growing back on his lip, but you can see scarring on the nose.
Hair growing back on the lip, so that tells me that accessory structure regenerated. But there's scarring on the bridge of the nose. That tells me that it wasn't complete regeneration. So I would agree with that answer. And that's often what the case is it's never both. It's never one or the other. It's some blend in between, right? Okay, I have one last video for you, and then we're done. I think you're going to want to watch this. This had nothing to do with this technology, but this is really cool tech.
And when it severely burns, the standard techniques that we have now, that takes weeks, months, sometimes. And the reason why people die is
Watch how stiff his hand is. Look at that.
good. So if we can find a way to get normal, healthy skin, as much of it as we want, within a week.
So that individual is a firefighter, the first one that you saw.
George Gerlach thinks he's found a way. A device for the deposition of skin cells on the wound.
It looked like something you see in Star Wars. This is Matt Uron, State Police Officer. He's one of the first people to be treated with the I attended a July 5th party at a friend's house, and there was a small bonfire. I was standing next to the bonfire, and an individual decided to throw a cup of gasoline on the fire. The worst part was my face. It was the whole right side of my face here, my ear, my neck, and my shoulder, and the entire top part of my arm.
Urim had suffered severe second-degree burns.
See the blistering?
This photo shows what a second-degree burn looks like.
The arm kind of looked like a piece of charred meat, like a hot dog that was left on a grill too long. The doctor said that I might be a candidate for this new procedure, which is a spray gun, and asked me if I would be interested.
Skin cell spraying is like paint spraying. Just you need a more sophisticated device like computer controlled. We isolate cells from the healthy part of the skin, the patient's own cells, which can be taken in a water solution, and that solution is prepared for cell spraying.
Basically, what they were doing was taking my stem cells from my skin and putting them all in the gun and spraying it on my arm.
Scientists have been able to regenerate sheets of skin for decades.
That's the dermograph I was telling you about.
For that skin to grow, and the new skin is
That's the old technology. This is the new.
Solves both of these problems.
It takes like 1.5 hours to take the biopsy, to isolate the cells, and to spray the cells.
This is what your skin probably looked like before treatment. This is what it looked like 4 days after it was sprayed with its own stem cells.
4 days. Yeah.
I did it on Friday, and my follow-up was that Monday, and Bernie had said it was healed, completely healed.
Though the skin gun is still experimental, over a dozen patients have already been successfully treated.
Pretty crazy, huh? All right.